Part A says it's a snowy day and you are pulling a friend along a level road on a sled. The sled and your friend together have a total mass of 55 kilograms. So let's start drawing this. There's my perfectly horizontal road. There's my sled. As you can see, I'm a fabulous artist. The mass here is 55 kilograms. So your friend and your sled are together in that rectangle. As you walk, you are pulling up and forward on the sled with a rope that is angled at 35 degrees above the horizontal. So there's the rope. There's your 35 degrees. If you pull with a force of 95 newtons, so we know the tension, you can cause the sled to accelerate along the flat road at 0.71 meters per second squared. So this is non-equilibrium. A equals 0.71 meters per second squared, and that's going to be going probably that direction. What is the coefficient of kinetic friction between the sled and the road? Good. So we're going to draw a free body diagram and identify all the forces. We have the tension, which is at that 35-degree angle. We're going to have normal force acting up and the gravity acting down, mg, where m is the 55 kilograms. And we were told that the sled is both accelerating and has its velocity towards the left, so that means if velocity is to the left, kinetic friction is towards the right. So that's our free body. Three of the forces are either vertical or horizontal, and only one is at an angle. So I am going to draw my x and y axes like this. Y going up, x going to the left. And then we'll know that a sub x equals negative the 0.71 meters per second squared, and a sub y equals 0 because the cart's not accelerating up or down. So let's make a little table of our forces, as those of you who know me know I like to do. We'll go counterclockwise here. Let's start with tension, clockwise, kinetic friction, and gravity. And let's just do the x and y components. And the easiest ones are the ones that are parallel or perpendicular to an axis. So mg has 0 in the x component and negative mg as the y component. The normal force is also got 0 in the x component, but now some unknown value, n going upwards, so that's an unknown. The friction, we always know that kinetic friction is always equal to mu sub k times the normal force, so I think I'll just write that in here, mu sub k times the normal force. So that's the same unknown as before. In fact, mu sub k I think is what we're trying to solve for. So find mu sub k. And it's got 0 in the y direction. So the tension is the tricky one. Let's draw over here our little tension again. Here's T. Here is going to be negative T sub x, because x is to the right, and there's our right angle, and this will be positive T sub y, and this is our 35-degree angle. So I'm thinking that the sine of theta, which is 35, is equal to ty over, which is the opposite over the hypotenuse, which is t. So that means ty is going to be t times sine of theta. And similarly, tx is going to be negative t times the cosine of theta. So that's all the components of the forces. Now we're going to add them up. And we're going to say that F net in the x direction is going to be equal to m times a sub x. And F net in the y direction, we have vertical equilibrium. A sub y is 0, so F net sub y is 0. This one is just equal to, so 0 equals t sine theta plus n plus 0 minus mg. So that gives us one of our unknowns here, solving for n. N equals mg minus t times sine theta. We know t, we know theta. So, in fact, we can solve everything here about n. If I plug that into my calculator, actually, I get 55 kilograms times 9.8 minus, the tension was 95 newtons, 95 times sine of 35. I actually get 484.5 newtons. So that's our normal force. The one we want to find, though, is going to be mu sub k. So let's look over here at the x component. I've got F net in the x direction equals m a sub x equals mu sub k times n minus t cos theta. I've just added up all the things in the x column. And solve for mu sub k, because that's our unknown. I'm going to have mu sub k times n equals m a sub x plus t cos theta, and mu sub k is equal to m a sub x plus t times cos theta divided by the normal force, which we found from before. So that is equal to 55 kilograms times negative 0.71 plus 95 newtons times cosine of 35, all divided by the normal force for 84.5. So I got that mu sub k equals 0.080. So that's the two significant figures, so we can actually write that right down here.